Hello everyone, this is a live stream, BUSN 6630, Spring 2021 Linear Programming. This lecture is over a technique, linear programming, and the first technique was forecasting, then linear programming. These are two very popular techniques in business, popular techniques in operations management. Okay, well first let's bring up the canvas. And in Canvas, coming down to here, notice we are in weeks 4 and 5, linear programming. And if you click on the weeks 4 and 5, notice I have the linear programming here. This video will be posted right here. And then next week, I'll have a video on quiz 2, homework 2, and then memo 1 coming up next week. So after this lecture, I will post quiz 2 questions, homework 2 questions, assignment 2 questions. All three of those will be over linear programming or constrained optimization, constrained linear optimization. Okay, so let's go back. Let's bring up the syllabus for a second. Let's download the syllabus here and open this up. Go ahead and open it up. And there it is. Edit, make this larger. So here we are, right here, February the 9th, linear programming. And so the homework 1 is due this weekend, on Sunday the 14th. So last week is when I went over quiz 1 and homework 1. And then next week I will go over quiz 2, homework 2, but I'll go over memo 1 also. So the memo 1 is just a communication of a memo and a video. So this is so I'll do that next week. Okay, just to set our bearings here on where we are, where we've been, and what we're doing. So we've done forecasting, a technique, and linear programming and optimization technique, and then next topic in aggregate planning, and then inventory, MRP. There we're getting into top-down to bottom-up type of operations, theory, strategy, techniques, applications, and we'll end with scheduling, which is very practical, and then I go into 2 techniques at the end. Okay, so I see people are beginning to queue up here, and so linear programming, then let's go back to Canvas. Whoops. Let's go back to Canvas here, to the home page. Okay, so down here in weeks 4 and 5, linear programming, we open up the weeks. And so today, and also I have the homework 1 and memo 1, but those are to submit the material. Quiz 2 is to submit the material. And so you click on the material here. Here's where you download the questions, homework, and assignments. And get all of them before you submit them. Okay. So let's download the linear programming Word file for the lecture. I've already done that. And so let's bring that up. Oops. There we go. Okay, here we go. So as I go through this, there's a number of things I'm going to be doing. One, in this lecture, I'll be looking at linear programming as a technique. The second, I'll be using Excel to solve linear programming problems. Third, I'll be looking at applications in operations. Now, one takeaway from linear programming is the technique itself, but much more importantly, and the reason I go into linear programming is not just the technique, but the concept of optimality. Because the concept of optimality can really be a key to instruct you on how to approach different problems, especially quantitative problems. And there's been a lot of case studies and examples and research to where people who don't use optimization to make decisions, then they do use optimization to help them make the decision. They make better decisions, But after they do that for a while and do the same problems over and over again, the optimization, the linear programming can teach them how to think optimally. So they have a good idea, again, a good feel for what an optimal solution looks like or should be, so they can do that even without running the program. So there's been quite a few indications of that, and a couple of people wrote papers on that, like certain companies have done that. So that's the biggest takeaway, is understanding optimization, get a feel from an optimal approach to some of the applications we'll be doing in this course. Okay, now I see a number of people are arriving here, so I think it's time to start. Okay, so let's get into this. Okay, first of all, I'm approaching this assuming no one knows linear programming. It's the first time you've experienced it. Some of you in your undergrad or background have had this before. I'm assuming no one has had this. So we'll start from the beginning and a little bit of background. First of all, the term linear programming. It's a very unfortunate term. The linear is fine, but the programming, it's not about computer programming. It's really about linear optimization, where you have a convex space and you have linear equations that create a space, and you find an optimal point within that space. So you do have a linear space, but the programming part, it's not really about programming. I think the concept of linear optimization, I'll say that, is centuries old. It's hundreds of years old. But no one ever used it in a practical way until computers came on board. When the computers came on board, then they had the ability then to actually solve large problems that required a lot of computation. And so they re-emerged, they resurrected the linear constrained optimization and put it on a computer, and now they can solve problems, larger problems, realistic problems, and there's where the programming came in. So you can take this concept and apply it. So one part is going to be the theory part of it. The other is going to be the actual application part. Okay, good. We have some questions here. Will you address any questions regarding questions? Yes, I will. I think I was going to do this at the end today because people are still arriving, but I could. Yeah. Oh, you're right. Both of you guys are right. Yeah, on quiz 1, I think there was I had a mistake, and I think. Yes, I think in the video I had worked it, and I had worked it and solved it, and then I said it was one answer, but it was really another answer. In other words, that which one, I forget which one, question 6 I think it was. I think question 6 got messed up. Let me make a note of it. And I think what I need to do is just, I think the answer was wrong, was somehow I got the wrong answer with the wrong problem, and the wrong problem with the wrong answer. Then I worked the one answer, then it got confusing. So I think when I just go through, the whole point of the quiz is to learn the mechanics. And so I want to go back for this question 6 on quiz 1. I'll just go back and change it all. And so since it was confusing, I'll just, if you missed it, I'll just give everyone that question as long as everyone understands it. Okay. So I get that all cleared up after this. So by tomorrow, you should see all that corrected. I didn't have a chance to because I was doing a lot of other things. Good point. Okay, we'll get that done afterward. Good. And as we go through, if you do have any questions, I usually will. Well, I can probably answer them as we go through. But I don't want to disrupt this flow of optimization because I have a lot to cover here. Okay, I'm going to start with a problem. Okay, linear programming. Start with a problem. The Redwood Furniture Company manufactures tables and chairs as part of their line of patio furniture. For simplicity, assume only 2 products are manufactured and only 2 resources are consumed. And those 2 products are tables and chairs. The 2 resources are wood and labor. They would like to know how many tables and chairs to make or produce or manufacture in a single production run to maximize profit but not exceed the capacity of the wood and labor. So every production run, they only have 300 board feet of wood, 110 hours of labor. How many tables and chairs can they make to maximize their profit, their total profit, where every table will give them $6 profit, every chair will give them $8 profit? How many tables and chairs should they make? What's the mix to maximize their profit and not exceed their capacity? What's the best way to use your capacity to optimize your profit? What's the best way to use your resources to optimize some objective? So this is a very common operations problem. Okay, now remember in forecasting I had a problem-solving approach. In linear programming, there's also a problem-solving approach. I'm only going to talk about 3 stages though. The first one is the definition of the problem. Now I think at the very first lecture way back when, I talked about understanding the problem, defining the problem. Well, the definition of the problem is extremely important, even more important in linear programming. Understand what the problem is. Now, this is one definition. And notice I have a definition in a sentence, in a paragraph. And then I've taken that and I've expressed that in a table. So there's really 2 different versions. Two different versions of the definition of this problem. One is a paragraph, the other is a table. Okay, so you can define a problem in multiple ways. And so recognizing a problem from a text, from a table, from a conversation, from a meeting is extremely important. So let's go on. Once I've defined the problem, the second stage is formulating the problem. Now remember I talked about transformation. You transform it into a different form, and this is formulating it into a form where we can solve it with some mathematical technique. Well, the technique we'll be using is linear programming. Okay, well, in the formulation of an LP, there's 2 steps. The first step should always be done first, and that is define your variables. Where T is a variable which represents the number of tables you're going to make. C is the variable which is the number of chairs you're going to make. Okay. Now the second step then is you take the definition of the variables and you take a definition of the problem and you put them together. Okay, so the whole point of the definition is coming up with a business question. And here it is. How many tables and chairs to make in a single run to maximize profit and not exceed the capacity of wood and labor? Now, I said that in a very specific way. I said it in such a way, let me highlight that is our business question. The whole point of a definition is defining a problem, defining relationships, and coming up with a business question. This is what we want. This is what we want to solve. Okay, so in this, what is going to be our objective? Well, how many tables and chairs are we going to make? That's our decision variables. To maximize profit. Okay, to maximize profit, well, every table gives me $6 profit here. And every chair gives me $8 profit. So if I have 6T and 8C and multiply that, that's going to be giving me my total profit. I want to maximize my profit. So that right there represents my business question of maximizing profit. This is referred to as the objective function. This is the objective function. This is what I want to optimize. In this case, we're maximizing. We could minimize. And we'll show you how to do that in Excel here before we leave tonight. Now, our variables up here in linear programming, these are the variables. Yeah, capacity is how much wood you have Oh, I'll get to it when I get to the constraint set. So these are referred to as decision variables. So the variables within, these are just terminology, these are decision variables that within a linear programming, because they are, the value of those variables is our decision. We are making this many tables, this many chairs. What's our objective? To maximize our profit. Now, we are also subject to something called a constraint set. Okay, so this is called a constraint set. Now, this is a set of relationships here that will define the constraint of the problem. Okay, so as we get into this, you say, okay, well, what does the 30 mean? The 30 means every table I make, one table requires 30 board feet of wood. Every chair requires 20 board feet of wood. Okay, so if I make one table and one chair, I'm going to be using up 50 board feet of wood. That's how much wood I'm using. But my capacity, that's how many board feet I have for this production run. In other words, that's how much inventory I have to produce tables and chairs. I can't produce tables and chairs that require more than that amount of wood, because that's my maximum amount of wood that I have to use to make tables and chairs. So that's the capacity of that resource, or that's how much wood that I have. Okay, likewise for labor. Well, every table requires 5 hours of labor, and every chair requires 10 hours of labor. So if I make one table and one chair, I'll be using up 15 hours of labor, but I have 110 hours of labor available in this production run. So a production run usually is defined as a week or 2 weeks or 3 days or something. And the amount of labor time you have, that's your capacity. That's how much you have. So you're limited by how much capacity you have. If you had unlimited capacity, well, to maximize your profit, it'll be an infinite number of dollars. But you don't have an infinite capacity. You only have 300 board feet of wood, 110 hours of labor. So for simplicity, I'm just looking at these two resources. Of course, there are other resources, but I'm starting simple to get the structure of the problem. Once I have the structure of the problem, then I can modify it, and we'll be doing that here in just a second, later in the next examples as I get to it. Okay, so let's put the constraints together. First, the wood constraint, this one right here. Well, every table requires 30 board feet of wood, so 30T is how much wood I'll be using when I make T tables in that production run. Well, 20C is how much board feet of wood I'll be using when I make C chairs. So this is the left-hand side. The left-hand side of my constraint. The left-hand side is how many resources I'm using. The right-hand side is how many resources I have available to use. So 1 is what I have available to use in this production run, the right-hand side. The left-hand side, that's how many I'm using. So what I use cannot exceed what I have, because you can't use what you don't have. So this is going to be, what I'm using is going to be less than or equal to what I have available. Likewise for labor. Every table requires 5 hours of labor. Every chair requires 10 hours of labor. 5T and 10C, that has to be less than 110 hours of labor that's available for this production run. Okay, so these are my constraint set. So I have two constraints right here, wood and labor constraints. Okay. Now, there's one more expression down here. Let me bring this down here. TC greater than or equal to 0. What in the world does that mean? Okay, well, it really means this. Okay, let's come back up here. and let's do this. Let's bring this over here and say T is greater than or equal to 0, and C is greater than or equal to 0. So everything we do in this course and a traditional LP, linear program, in business, your decision variables, T and C are your decision variables. Your decision variables are always constrained to be 0 or greater than 0, either 0 or positive. So our decision variables must always be 0 or positive or non-negative. So these two constraints right here are referred to, as non-negativity constraints. And so we will always, in everything we do in this course, we will always have non-negativity constraints on the decision variables. Okay, so there's two of them. And why there's two? Because we have two variables. So we have two variables because we have a Cartesian coordinate system. We have an x and y. Can you have more than two variables? Of course you can. Then you have 3 dimensions, 4 dimensions, 5, 10 dimensions. We'll have 6 dimensions here in a minute. Okay, so we will always have non-negativity constraints on every problem we work in linear programming in business. Now, some of you may have learned linear programming in other disciplines like engineering or mathematics or some kind of social science. And sometimes, like I know in engineering, the non-negativity constraints are not common. They're not required. Instead of non-negativity constraints, they're called free variables. They can be positive, negative, 0, anything. We don't do that in business. Everything is non-negative. Now, if you have a variable that can go negative, that's a decision variable that can go negative, then you have two variables, the positive side and the negative side. We don't do that in here. That goes a little bit beyond this course. Now, since we always have the non-negativity constraints, sometimes I write it in shorthand. And that's exactly what this is. The T and the C, both of those are non-negative, or greater than and equal to 0. Okay, and sometimes I don't even put them in at all. Sometimes they're not even there. I don't write them down, but they're always there. They're always there. So let's bring them back. Let's bring this back to where it was before, so we can continue on. Now let me come to some of these questions and see if I've answered all of them. Capacity. So max would be with unlimited capacity. Well, max would be infinite with no capacity, but with capacity, then you'll have a finite solution. Since notice that these, Craig, who's asking this? Craig. Okay. I think from your questions, Craig, and your background, when you have less than constraints and the variables are non-negative, you're going to have a convex space. When you have a convex space, when you have a convex region, then you're always going to have a unique solution if you have a linear function that you're trying to optimize. And there's a linear optimization. So when you have these constraints, you'll have a finite solution. Okay, I think capacity is a total they can accommodate. They have 110 total available in space to store space to store 300 board feet of wood. No, they only have 300 board feet of wood to make the tables and chairs. They might have enough for 1,000 board feet of wood. They only have 300 for this next production run. It's kind of like we have a warehouse that we can store 100 million doses of coronavirus, a vaccine, but we only have 100,000. That's a capacity. That's all we can do because that's what we have. Okay. At least that's maybe not a good example, but that's the idea. Let's see. Okay, good. So now, the first is defining the problem. By the way, defining the problem sometimes is the most difficult step. What is the problem we're trying to solve? And sometimes it's extremely difficult. And you'll see on like probably in the memo, in this memo, second memo, or some of the problems that I'll give you in the homework, in the homework part. Not the quiz part, but the homework part. And sometimes it's really difficult. What are we solving here? No, let's solve this. No, let's solve this. Oh, okay. Well, sometimes this is really important, and sometimes it's difficult. Now, once we have this, the formulation, got to be careful and formulate it correctly. But once we have it formulated, then the third thing is, now let's solve it. Now here comes the mathematics. And notice the mathematics, again, is the third step here. It's not at the beginning. It's once you've defined the problem, you formulate it correctly, then you solve it, okay? And by the way, there's different ways of defining this problem. And even from this definition, there's different ways of formulating it. And from this formulation, there's different ways of solving that formulation. I'm going to be using linear programming because that's the title of this topic. But you can solve this set of equations with different techniques. Okay, we won't go into them, but you certainly can. Okay, well, there's going to be two ways of solving it. One is the graphical method. You're not going to be doing that, but I'll be doing it just to show you visually what's happening, so you can understand the concepts. But then we'll be using Excel over here to solve it. And here in a minute, I'll go into Excel. Like the next page is the LP using Excel, and I'll solve in Excel, show you how to use it, and that's what we'll be doing today and next week, this next 2 weeks. I'll show you how to do it step by step by step. Okay, but graphical. Okay. Well, the idea here is we have two constraints, a wood constraint and a labor constraint. What we can do, let's say that the y-axis here is the I think it's the tables. Let's see here. Yes, the y-axis is the tables. No, the y-axis is the chairs, and the x-axis is the tables. Okay. For example, if I solve this equation, I'll have C is equal to, and then I'm going to have 300 divided by 20 minus, 300 divided by 30, times t. Okay, so right here, 300 over 20 is 15, right? So if t is 0, then if I make zero tables, then how many chairs can I make? Well, 20 into 300 is what, 15? So I can make 15 chairs right here. With 0 tables, I can make 15 chairs with my 300 board feet of wood. But if I want to start making tables in addition to chairs, well, every table I make, I have to use up, what's 300 over 30 is 10. I'm going to use up 10 board feet. So I'll be taking 10 board feet away from this 15. So every table I make, the amount of wood begins to decrease. I can make less, the wood decreases for how many chairs I have. And so this is going to decrease like this. So this equation is this line right here. Okay. Now, everything to the lower left of this line, I can make less than 15 tables. Less than 15 chairs. If I make 0 chairs, if this is 0, then how many tables can I make? I can make 10. So connect those lines, and everything down here I can make. Everything above this, I don't have enough resources to do it. So this gives the boundary of how many tables and chairs I can make given my wood constraint. But I also have a labor constraint. So if I make 0 tables, how many chairs can I make? Well, 10 and 110 is 11. I can make 11 chairs. But if I have 0 chairs, how many tables can I make? Well, 5 and 110 is 22, way out here. So there is my boundary of how many tables and chairs I can make with just my labor constraint. Okay, and so I can solve this for C again, since for this equation here. That's going to be 110 divided by 10, and then minus 110 divided by 5. Okay, and so all I'm saying here is I can plot these two lines, and this first line for wood, there's my wood constraint. My second line for labor, there's my labor constraint. So visually, you can see what's happening here. So now I want to maximize 6T and 8C. Okay, that's my profit. So if I make 0 tables and, let me breathe this down. If I make 0 tables and 0 chairs, then my profit is 0. If I make 1 table and 1 chair, then my profit is going to be 14. But 1 and 1, it's going to be like right in here somewhere. And so this graph here shows you how many tables and chairs I can make. And so what it does here is says, well, what's the maximum number I can make? Well, the maximum number, you're going to go to one of these corner points. One or more of these corner points will be a solution. Okay? Now, as it turns out, these corner points are called extreme points because it's the extreme corners of this region in here. But everything within this region, but notice this region over here, well, I have enough labor, but I don't have enough wood. And this region in here, I have enough wood, but I don't have enough labor. So this region in here, I have enough wood and labor. So it's in this region right here. So this region in here is referred to as the feasible region. Okay, so the feasible region is defined by the constraint set. In other words, all the points which satisfy all the constraints, there's 4 of them, all the points, the region of points which satisfy all the constraints define the feasible region. Okay, and when you start maximizing or minimizing, right now we're maximizing our objective function, then what's going to happen is that, well, the maximum, what if our objective function was 6T? What's the maximum number of tables can I make? Well, this is tables down here. The maximum number of tables I can make is going to be right here, 10, 0. Right? And so my profit will be 60. But then let's bring this back. Now, what if my objective function was just chairs? What's the maximum number of chairs I can make? Oh, I can make the maximum number of chairs if T is 0 is going to be, we said, 15. I can't make more than that because I don't have enough labor. Okay, so we'll bring that back. So if I was just making tables, I can only make 10. I can't make more than that because I don't have enough wood. If I just want to make chairs, I can only make 15 because I don't have enough labor. Okay, because this is the maximum labor. So what if I have both labor and wood? So as it turns out, the optimal solution, the maximum is going to be this point right here, again, which is a corner point. So the solution to an LP, if it exists, will always contain one or more of these corner points. So that's of the feasible, and the corner point has to be feasible. So that's a corner point because it's feasible. That's a corner point because it's feasible. That's a corner point because it's feasible. And 0, 0 is a corner point because it's a corner of that region. Here's a feasible region. We have 4 corner points. Now that is not a corner point because it's not feasible. Okay, and so it has to be feasible. Okay, and it has to be on the corner. It has to be on the boundary at a corner point or an extreme. Corner points is one version of what is called an extreme point. Extreme is the extreme of the feasible region. That achieves optimality. I divide through by 20. I solve this equation for C, and I make it an equality. So I divide through by 20. So 300 over 20 and 30 over 20. Oh, sorry. That should be 20. So I divide everything through by 20. 300 over 20 and 30 over 20. There we go. So I'm taking this constraint set and expressing it then as a graphical line. Okay. Now I did this quickly, and I didn't do it in such a way that you're going to have to do it, because you'll never be doing this in this course. You can if you want to, but there's a lot of textbooks that will explain this, and I don't think it's that important for this course to know how to do this from start to finish, but I did it enough to know what it's saying and what it's doing and what's the concept. Because we'll be using this graph quite a bit today on optimizing. Okay, for example, if I use Excel, I can put my coefficients of 6. Here's my variables up here. I tell you what, let me do this. Take that out, take that out, and take those out. If I type this stuff into Excel, correct, Sridevi. If I type this into Excel, take this 6, 8, my objective function, and put it right here. Take my constraint set 30, 20, and put it here. 5 and 10, put it here. And then 300 and 110, and put them over here. Okay. Now, my values here, this is the value of my decision variables. This is how many tables I'm making, how many chairs I'm making. Well, the value of my objective function then is my tables times 6 is how much profit I'm making by making T tables. And this is how many chairs I'm making. But the tables and chairs will also say the left-hand side of how much wood I'm using, the left-hand side of how much labor I'm using. So, okay, what does make it feasible? What feasible means is that every point in this region will satisfy all these constraints simultaneously. So every point in this region then would be a candidate for a solution. Okay, and so we want, so the linear program is a point in this region, in this region, which satisfies all these constraints at the same time. That point or points which yields a maximum for our objective function. That is the solution to this linear program, and we'll call it an LP. Okay. So this region here is called a feasible region because every point in this region is a feasible point, feasible to be a solution. Doesn't mean it is a solution, but it's feasible. Now, if we have a point outside of the region out here, then that is not a feasible point to be a solution. So it cannot be a solution. It's not feasible to be a solution because it doesn't satisfy all these constraints. So this point in this region will satisfy the labor constraint, but not the wood. Over here, the wood, not the labor, this kind of thing. Okay, so I do have another video that I go through this step by step, but I didn't think I should do it. I didn't think I needed to do it in this course, but maybe I should have to bring us all on the same page. That might have been helpful. Okay, I thought I could say it quickly, but I've said everything, but I didn't do it step by step. That's right. The feasible solution doesn't mean it's optimal. It just means it's possible. It's feasible. Okay. Now, to solve this, let's use Excel. But what I want to do today, this evening, is actually show you how to use Excel. So let me bring up Excel. Okay, let's bring this down a little bit. Let's enlarge this. Okay. We don't need this. Okay. So what I did here, let's reduce this a little bit more. Let's bring this over here. See if I can format this where you can see it. There we go. I think that's going to be good. Okay, now then. So I'm going to, this right here, I typed it in. All I did was just type this in. So all this is just typing. Okay, let me take this out. Okay, so what I want to do is set this up in Excel. First, you type it in. Next, these are going to be my variables. Okay, now what I want to do then is to say, well, you know, to be clear, to know exactly how I'm going to be doing this stuff, let me take these two cells. Let's come up here, and this little paint can will shade the area. Let me shade it. Let me make it a little deeper. Boom. Okay, that shaded area, those are my decision variables. Those are the values of my decision variables. So those are going to have how many tables I'm making and how many chairs I'm making. So over here, this over here, and let me box this in, okay, especially this one here, okay. Over here, this is going to represent my objective function. What's my profit? Well, that's going to equal 6 times the number of tables plus 8 times the number of chairs. Okay. And so let me left justify this so we can see it. There we go. So notice I have, here's my coefficient, like in my objective function up here. There's my coefficient, 6 times my number of tables is C5, 8 times the number of chairs. So it's going to do this arithmetic, and whatever that arithmetic is, it's going to put it in that cell, which is going to be my profit. So if I make one table and one chair, I have $6 profit, $8 of profit, total of 14. If I make 2 tables and 1 chair, it's 12 and 8, which is 20. 2 and 2, etc., etc., etc. Okay, these are my decision variables. Let me delete them. What I want is linear programming to put a number there and put a number there such that that is going to be a maximum value. Now, if I solve this the way it is, it would just say infinity. But I'm constrained. I'm constrained by my wood and labor. So that's going to be the values over here. This is going to be the left-hand side of my constraint set. So this is going to equal, Becca, 4 and 9 is where they intersect. That's an extreme point. That's optimum for this problem. That's true. That is the optimal solution. But that's not always the optimal solution. And I'll show you why here in just a second. So to solve this, again, I want the coefficient, 30, times t plus 20 times c. Okay. Now, if you remember, there are some functions, and I'm going to be doing, if you do this, you notice it's 30 times t plus 20 times c. But that type of multiplication, and addition is so common that Excel has a function. And the function is called the sum product. The sum product, to where I'm saying, okay, I want these two, comma, and these two, in parentheses. Okay, now, what I'm going to have here is I want to say C8 and D8. So I have two numbers here, comma, C5 and D5, that's the red. And so when you have two arrays like that, it'll take 30 times this, 20 times this, and add them together. So it makes it very easy to compute a large number of constraints. So now the C5 here, the red here, I want that to be fixed. So I'm going to highlight C5 and D5, F4 to fix it. And then what I can do is just copy that down. Okay. So now I only have 2 constraints, but since I can copy this down, I can copy this down and have 5, 10, 15, 20 constraints. It's very easy to do now that I have it set up. Okay. Now, right now I have it set up. It's ready to go, right? But then how can I make Excel give me my solution? Okay, well, this is an add-in over here called Solver. And the Solver is an optimization add-in. It has linear programming embedded in it. And so it's an add-in. So if you don't have it, then you come up into, I'll do this quickly here. I click File, come down to Options, come over here to Add-ins. It's an add-in. Now then come down here to Add-ins and make sure you have Excel add-ins. Say Go, and it's going to come up with Analysis Tool Packet, Solver add-in, the Solver add-in, that's what we want, and then click OK. I already did it, so if you click OK, what will happen is under Data, over here at the right, you'll have Analyze, and under the Analyze, you'll have a Solver. So let's click Solver, and it comes up with a window. Now in this window, it's going to say, okay, tell me what your decision variables are, what your objective function is, what your constraints are, and I'll give you an answer. Okay. The first one here, set your objective. Okay. The objective is going to be right there. That's my objective function. That's a cell which has a value, and that value is the value of your objective function. That's my profit. Okay, that's what I want to optimize. But when you say optimize, you get to maximize it and minimize it. I want to maximize it for this problem. So to set my objective in order to maximize. I could minimize it. I could also set it to a value. Okay, and I think I do this in my stat course, but I don't do that here. So we'll just do max and min in this to keep it simple. By changing variable cells. Well, if you're going to be changing the cells, those are your decision variables. I've highlighted them. So I click there, my cursor there, click that, come over here, left click and drag, and there's my decision variables. C5 to D5, and there they are. Okay, I have my objective function, E6, I have maximize, I have the direction, I have my decision variables, now my constraint set. So let me add a constraint. Add a constraint. So when I added, okay, let me cancel, go back. Under constraints, subject to constraints over here at the right, add, change, delete, reset all. Okay, let me add a constraint. Boom. I add a constraint and it says the left-hand side is the cell reference, the right-hand side is the constraint. Aha. The left-hand side is the cell reference. Well, the left-hand side is going to be a cell. It's going to be, let's say this one, has a value of the left-hand side of a constraint. So therefore, the left-hand side always contains variables, the decision variables. The right-hand side always contains a constant. So let me cancel this. Let me close this out. I'll open it up again in a minute. So the left-hand side always contains my variables. The right-hand side always contains constants. Now, when the left-hand side has variables, the right-hand side has constant. That's called canonical form or standard form. We will always, when we formulate it, when we define it and formulate it, we'll formulate it to where we'll have standard form. Because the standard form will go right into Excel. Okay, let's bring the window back. Okay, let's add it again. The left-hand side is less than or equal to. So right here, I can have less than or equal to, an equality constraint, greater than or equal to. I can have integer, binary. I can have different types of relationships. In this course, we'll just have less than or equal to, equality, and greater than or equal to. So this is less than. There's the direction, so less than. And click that. The right-hand side, I click there. I want a value which is 30, 300 I mean. Now, and notice that is a cell which has a value in it. And that's my constraint. Let's back up. I can put the number in there if I want. It'll take it. Or you can put a cell in there. And the cell has a value. Okay? But the cell over here, this cell, must be a value which is connected to the decision variables. This could be a value which is connected maybe to other things. But the left-hand side must be connected to the decision variables in order for this for it to recognize that it is a constrained optimization problem. So it does that for you. Well, that's a wood. Well, now we have a labor constraint. Let me add another one. The labor constraint left-hand side there. Okay, and then it's going to be less than or equal to. I didn't have to do that. The right-hand side is 110. I don't have any more to add. I say OK, and it comes back, and there's my two constraints. E8 is less than or equal to G8, and E9 here is less than or equal to, whoops, I did the wrong thing. E9 is less than or equal to G9. So I have them all there. Okay. Now, notice I did not put in my non-negativity constraints, but they're there. And Excel and Solver knows that. So below my constraint set, right here it says make unconstrained variables non-negative. Now notice T and C are our unconstrained variables. They're allowed to move around. But then you say no. If we click this, we make them non-negative. So in this course, we always have non-negativity constraints. We always click that. In other applications, you may not, but at everything in business, we do. Okay, select a solving method. Notice they have three different kinds. They have a nonlinear method. That nonlinear is just a search algorithm. The simplex LP, that's what we would be doing in this course. Pretty much everything we do is a simplex. I teach a supply chain course. We'll do the other ones. We'll do search algorithms. We'll do other things in my other courses. But this one we'll keep it just linear programming. Okay. Now when I click solve, we've already seen the answer. It should be 4 tables, 9 chairs, with a profit of $96, and this is 300. This is 110. Those are the numbers that should be there, right? So when I click solve, if I set this up correctly, then that's what we should see. Are you ready? I hope it does it. It doesn't always do it. Sometimes I do something wrong. But let's try it. Here, ready? 3, 2, 1. Boom. Oh. Solver found a solution. All constraints and optimality conditions are satisfied. Keep the solution. Well, if we found one, yeah, we'll keep it. I say OK. And there it is. 4 tables, 9 chairs, $96. Isn't that exciting or what? And so let's bring this back. And there we have it. 4 tables and 9 chairs, $96, 300, 110. Boom, we solved it. Now I went through that nice and slow. I'm not going to go through it again. This is the only time I'm doing it. Okay, so for the rest of today and next week, I always say, okay, we'll do this, 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 and move on. So I did it slowly so you could see exactly how to set it up. Okay, and so this will be the first LP we do in here. We'll do a lot more. We'll do a lot more today. Okay, so down here, here's my formulation. There's my Excel solution. And so right there, you can see there's the second step and the third step. And so a lot of what I'll be doing in the quiz is just the interpretation of the formulation and a little bit on the application. On the homework, then I'll be going back to giving you a definition up here, getting a formulation, and then solving it with Excel. Okay, and then the memo is expressing it. Solver add-in is in the inactive application add-in and my options add-ins. Oh, okay. I think that's okay. Okay, so what I just did was this next example 1 solution using Excel. I typed it in exactly how to do each one. I've already showed you how to do it. This video and this page to go through reading it and seeing it. Hopefully everyone should be fine on doing it. If not, you're going to see it a lot of times. Okay. Now the sensitivity report, we're not doing that initially. We'll do this probably next week, not today. Okay. Now let's take an extension. Now let's take this redwood furniture problem and extend it before we do some applications. Okay, here we go. What is a fixed cost? Here's a really good extension. In other words, the redwood furniture problem says we have this much wood, this much labor. Well, if we use it, then we will pay for it. Okay, it's in the profit. But what if we have wood as a fixed cost where we buy it and we pay for it whether we use it or not? Okay, let's let wood be a fixed cost. Let's break this profit up into revenue and cost, where we have a fixed cost and a variable cost, where labor is a variable cost. We'll pay them if they're there. If they're not there, we don't pay them. But the wood, we buy it. Okay. Okay. The fixed cost is let's say that our unit cost is $1.30 per board foot at 300 board feet. That's what we're going to buy. Is a fixed cost of $3.90, and that $3.90 is going into our objective function as a constant. Minus our profit is minus $3.90 is cost. Okay. Our variable cost is of the labor. Let's say it's $6.40 an hour. This is an old problem. It's really small labor cost, but let's just go with the numbers. Since I have cost, I need revenue. So my price of my tables I picked is 77, chairs of 98. I just arbitrarily picked those numbers. Okay. Now, what's my unit variable profit? In other words, if I start making tables and chairs, what's my variable profit? I know what my fixed cost is. What's my variable revenue? Okay. Well, right here, I have for each table, one table, I'm going to have $77 of revenue minus a variable cost of $6.40 an hour times 5 hours. Why 5 hours? Well, remember, in the formulation, every table required 5 hours of labor, and every one of those hours cost $6.40 an hour. That's my wage, $6.40 an hour. So I multiply that, and so for every table I make, I get $77 of revenue. I have a variable cost of whatever 5 times 6.4 is, and my variable profit is 45. That 45 then, that's in my objective function, 45 times T. I do the same thing for chairs, where I take my price of 98. I subtract my variable profit of $6.40 here, times 10 hours of labor for every chair, and it's 34. That 34 goes in my objective function. So now this right here, this function right here, goes right into that cell in Excel. Now, I'm not going to be running Excel again. I'm just going to saying I'm going to put these in there, and I'm going to run it. In other words, the 45 and 34 are put here. This equation, those numbers are put there. Those are my coefficients. This equation is put here. I run this thing. I say go. I say solve, and it'll solve it. And there's my 4 tables, 9 chairs, and $96. Okay. Well, the value of this is to make it more realistic. And this, remember I said to keep it simple, let's assume 2 products, 2 resources. Well, one way of building models is start simple and keep adding to it, adding to it, adding to it to make it more realistic. And here's an example of that. Modification 2. Well, I could stay here a long time, and maybe some of you don't want to be here this long. Oops. Bring that back. Let me bring this back. Oops. Bring this back. Wow. This thing is really getting exciting with moving things too fast. It doesn't like me to move that fast. Okay, so let's come over here. In other words, where am I? In other words, I'm just using the using this. Instead of 6 and 8, I have 45 and 34. 45, 34. And this right here is going to equal, let me left justify again. Okay, equal this, well, I don't want this in here because I want to solve it. This is going to equal this times this plus this times this minus 390. I said I wouldn't do this anymore, but I guess I am. Sorry about this. I just get excited. I want to solve it. And so it'll give me the same solution. Okay, I just want to show you that it does work. Okay. Okay. What happened here? Okay, somehow my screen went black, and I don't know why. This has never happened to me before. No source. Okay, I've lost the source. Okay, I'm streaming, but I lost my source.